All right, so the next reaction we're going to learn about from the chapter 22 is alkylation of alpha carbons. And let's take a look at how that's done. It's a pretty simple reaction. I like this one because it's very intuitive. First thing you do is you take a ketone or an aldehyde that's enolizable, meaning it has alpha protons. You treat it first with a strong base, and I'm just going to keep it as generic base. And then in step 2, you treat it with an alkyl halide. And ultimately, all you're going to do is an SN2 reaction where that enolate will attack the alkyl halide and kick off a leaving group. So it's pretty basic chemistry, but let's see the mechanism. So, like I said, we have alpha protons on either side. Doesn't really matter which side you grab because it's symmetric. This base typically is a pretty strong base. So we'll steal one of these alpha protons. Make our enolate. And just like before, I said we would do an SN2 reaction. And by doing this, we're able to make a new carbon-carbon bond. Does that make sense? One thing to remember with these alkyl halides is you have to be careful about their size. What happens if you use a tertiary alkyl halide? It won't do SN2. What will likely happen instead? Not quite. Be an E2 reaction, right? So if you've got a tertiary alkyl halide and a strong base around, you're going to favor E2, not SN2. So this ideally should be primary or a methyl alkyl halide. Otherwise, if it's secondary or tertiary, you favor E2, you don't get the substitution product. So you do have to keep that relatively unhindered. All right, now I've got a trickier problem for you. Let's assume our starting material is not symmetric and you have two different types of alpha protons. So in this compound, I have a methyl group over here, and I've got a blue alpha proton over here, and I've got green alpha protons on the left-hand side, right? I've got two options. One is my base could grab this blue proton and give me this enolate. Or you could have your base, sorry, these bases should be stronger, have negative charges. Your base could grab one of these green alpha protons and form the enolate on the other carbon. All right, now the question is, which of these is more stable and why? Blue because it's more substituted. There's also another way we could explain this, right? So let's draw the resonance structures. I just have to say resonance and you know. Let's do this one too, just to compare. So we've got these two resonance structures. Now the question is, which one's more stable? And Dylan already said the top one's more stable because the carbanions on the more substituted carbon. What about the alkenes, though, if we draw the other resonance structure? Yeah, if we look at this alkene right here, you notice how it's tetrasubstituted. We know more substitution makes it more stable. So this enolate is the thermodynamic enolate. If you remember, thermodynamic means most stable. All right, The bottom one, though, if you think about a base and you have to steal an alpha proton, those green ones are just simply going to be easier to pluck off because it doesn't have a methyl group blocking the approach of the base, right? So the bottom one isn't more stable, but it's kinetically more accessible. So let's label this one. This is our kinetic enolate. Its alpha protons are more accessible. I'm going to change my parentheses here. Does that make sense? All right, so let's imagine you've got a itty bitty little base, doesn't take up much room. Which of these enolates do you think will be favored, the top one or the bottom one? Top one, right? So if you're a small base, you don't really care which alpha proton you're going after. You just want to form the most stable product, right? What if you're a super big, bulky base that takes up a lot of room? Then the bottom one's probably going to be more favorable because you're going to have a hard time reaching that blue proton because it's hidden next to that ring and methyl group. So it's going to be harder for big bases to form that thermodynamic enolate. But let's take a look at the products that result from this, just so that we finish up our full synthesis. And so, for example, in this reaction, you could show this clamping back down attacks this R group. And when you do this, the R group is going to come off the right-hand carbon. So I'm just going to show the R group right here in blue. And we regenerated our carbonyl right there. Then for this one, same thing, but now it's going to come all the way around from the left-hand side. Oops, and you get the R group coming off the other position. Does that make sense? So let's make a few notes just to kind of describe what we're seeing here and what we hypothesized. Bulky bases favor formation of the kinetic enolate. That's one thing we previously said. If we're trying to form the kinetic enolate, is it better to run things at really high temperatures or really low temperatures? What do you think? Low temperatures. If you remember back to last term, we said typically if you want the kinetic product, you want to run it under cool conditions. If you want the thermodynamic product, you just want to crank up the heat. So for this one, bulky bases favor formation of the kinetic enolate, and the kinetic enolate is favored at low temperatures. So an example set of reagents you might use would be lithium diisopropyl amide, that's LDA. And then often it's run at negative 78 degrees Celsius, so quite cold. Does anybody know why negative 78 degrees Celsius is really common in organic chemistry literature? Not sure if anybody would know this off the top of their head. Good bar trivia. It's the temperature that acetone gets to when you huck in dry ice. Practically every organic chemistry lab in the world has acetone and dry ice on hand. When you mix those two together, it's reliably negative 78 degrees. It's very convenient to carry out. So typically you have that big bulky base, LDA, and then you've got a dry ice acetone bath to really keep it cold and to favor the kinetic enolate. So that's the first one. And then the second one is small bases. So small unhindered bases at moderate or high temp favor the thermodynamic enolate. And an example set of reaction conditions for this would be something like sodium hydride. Sodium hydride is a nice small unhindered base, and quite often this can just be done at room temp. You don't even need to really crank the heat up. Room temp's enough heat. Does that make sense? So let's just write down the reaction conditions so we have a really simple generic thing to look at. So we'll use that same starting material we were looking at before. For this one, we want the R group to come off the more substituted carbon. That means we need to go through our thermodynamic enolate. So I'd say NaH at room temp. And then you need your alkyl halide. Where for the bottom one, our kinetic enolate, we want it to go off the other alpha position, and that's where you would use LDA at negative 78 degrees Celsius, followed by your alkyl halide, and then you get it attached onto the different position, or the opposite alpha carbon. Does that make sense? So we do have the control to affect which carbon gets alkylated. All right, the next reactions are similar to alkylation reactions. The first one is called the Malonic Ester synthesis. And I'll show you the overall reaction first. So you always start out with an alkyl halide. In fact, I'm going to color code this as a blue R group. And you have some sort of leaving group. I'll call that X. And after a few steps, you end up making this product on the right. So really what you're adding is a CH2 and a carboxylic acid. So it's a pretty clever alkylation strategy, and I'll show you how it works. So the first thing you need is diethyl malonate. And diethyl malonate looks... Yeah. No, thank you for letting me know. Sometimes I get carried away with excitement. I just love chemistry so much. So if you remember talking about malonic acid, that was one of the diacids. This is the ester derivative, so you've got ethyl esters on each side rather than carboxylic acids. That's why it's called diethyl malonate. And in the first step of this reaction, you actually need to enolize the diethyl malonate. And this works very easily because these interior alpha protons are really acidic. Why is that? Alpha to 2 carbonyls, exactly. So it's got resonance stabilization across 2 different oxygens. So we'll show the enolization. Once you've enolized it, then you treat it with the alkyl halide, so that R group in blue up above. Let me change this. So just like before, I'm going to keep that R group blue so we can keep track of it. And just like I mentioned before, this should be primary or methyl. If it's tertiary, you get E2. Okay, so now we've got that alkyl halide. We can do our SN2 substitution, kick off that halogen, and we'll alkylate the diethyl malonate. So we've got this R group dangling off that central alpha carbon. All right, so now a little bit of review. What happens to esters if you treat it with strong acid? Yeah, if you remember back to the carboxylic acid chapter, if you treat any sort of ester with strong acid, you can actually hydrolyze off those esters back into carboxylic acids. So I'm not going to show all of those steps, it's just review. Yes, it's in last chapter's notes. And so we've hydrolyzed both of those esters into carboxylic acid groups. All right, now what I'm going to do is I'm going to redraw this a little bit differently. And you'll see why in a second. So I'm just going to put the equal symbol here. The carboxylic acid on the left-hand side is going to stay put, but I'm going to spin around the one on the right so that the carbonyl is pointed out. And then the R group's pointed down. And if you remember, I said some of these carboxylic acids are quite stable in this conformation. And why is that? Yeah, you've got hydrogen bonding that can occur here, right? So in reality, it prefers to adopt this conformation to have that intermolecular H bonding capability, and you're forming a six-membered ring, which we know is really stable. So you have this intermolecular H bond. And then in the next step, you apply heat. And when you apply heat, you actually do something called a decarboxylation. And in a decarboxylation reaction, what happens is you lose CO2. So now we need to draw the arrow pushing to account for the loss of CO2. So for example, in this one, you would say, all right, this is going to come up here, form a bond to that hydrogen. This is going to clamp down here. It's going to kick off over here. So now when we go ahead and draw our product, we still have the alcohol on the left-hand side. The oxygen carbon bond is now a single bond, and it's bonded to hydrogen. It stole that hydrogen, right? We now have a double bond down here to that alpha position. We still have this R group dangling off right there. And then what do you think happens to this? Well, I gave you the hint previously. It's going to get blown off as CO2, so it gets completely ejected off. All right, what sort of functional group is this? It's got both an alkene and an alcohol. What do we call those? Oh, not quite. Be an enol, right? So half alkene, half alcohol. So this is an enol. Are enols typically happy being enols? No, they want to tautomerize into their keto form. I'm not going to show this full mechanism, but make sure you are comfortable going back and forth. And when you do this, you're essentially just shuffling protons around. And you get the R group installed right there. And like I said, this is a tautomerization. So this would be your final product. Does that make sense? And if you notice with the final product, we added not only the carboxylic acid, but that CH2 spacer as well. So we added that entire chunk in this process. Make sense? A little bit. Some skeptical looks. All right, let's take a look at what happens if you dye substitute it. So just like in the previous reaction, you can start out with diethyl malonate. This time we want to alkylate it twice. It's going to be a little steppy. First one, we're going to treat it with strong base. I'm going to use the same base that corresponds to that ester leaving group, just like before. This time I'm going to alkylate it once with this alkyl halide where the carbon is red. Or sorry, it's blue. The pen is blue. And then in the second one, you treat it with base again because you do have a remaining alpha proton, right? And then in step 4, now you treat it with the red carbon and the halogen. So you can really alkylate this twice if you want. So we've substituted that alpha position. We don't have any more alpha protons, so we gotta stop here. And then in the next step, we're gonna treat this with acid and heat. And if you remember, with acid and heat, the first step is you're gonna hydrolyze off both of these esters. And then the other easy thing to remember is after you've done that, this will get lost as CO2. So I'm kind of showing you my tricks that I use for remembering this, but it's always important to remember you lose 1/2 of it as CO2. Yeah, either side. It doesn't really matter which side pops off as CO2. So for example, our final product with this one, without drawing the full mechanism, will have an OH here. You'll still have a red carbon on that alpha position and a blue carbon off that alpha position. So this would be your final product if you decided you wanted to do this twice. So let's do a quick comparison. Because I like relating this to previous chemistry we learned. So we'll compare this to this one. Actually, sorry, I'm going to draw this slightly differently. What I want your help with is remembering what reaction conditions we need to accomplish that top transformation. So in this one, we need to swap out a halogen for a carboxylic acid. Who remembers what reagents we can use to do that? I heard a CO2 something. So the first thing I would do is turn this into a Grignard reagent. So step 1, you could add in magnesium. Step 2, you can add in carbon dioxide, the dry ice. And then step 3, you can add in your acid, right? This allowed you to install just a carboxylic acid group, right? Or for the next one, the one we just covered, we said if you want to have that CH2 spacer, you can do this workaround. Whereas for step 1, you treat it with a strong base, like sodium ethoxide. Step 2, then you treat it with your alkyl halide. Then step 3, you treat it with acid and heat. The main difference here is with this one, you have that CH2 spacer. Does that make sense? So it's kind of building off of chemistry we've previously seen. All right, we've got another one that's really similar to this. This is called acetoacetic ester synthesis. It's a mouthful. So let's take a look at that one. This one's very similar mechanism. And just like before, I like looking at the overall synthesis. So just like before, we have our blue carbon. And this time, rather than a carboxylic acid, you're actually just going to have a ketone installed with the CH2 spacer, so specifically a methyl ketone. All right, so let's take a look at the mechanism. Mechanism is very similar to what we previously saw. However, instead of using diethyl malonate, we're going to use a different starting material. That's half ester, half ketone. And just like before, we're going to treat this with ethoxide. We're going to pluck off one of these alpha protons. Yep. The alpha protons in the middle are way more acidic than the alpha protons on the outside, so it's not even going to be close. Yeah, good question. So those interior alpha protons are double resonance stabilized. They're going to get plucked off first. And then in step 2, just like we saw before, this is going to do a substitution reaction with our alkyl halide. So our enolate's going to attack, kick off our leaving group. Now we've got this R group hanging off here. Just like before, I'm going to skip the hydrolyzation step. But anytime you treat this with strong acid, you can hydrolyze your ester. So this ethyl group is going to pop off and you'll convert it to a carboxylic acid.
Are we allowed to show it like that at skip steps?
I'll try to give you specific directions. There may be situations where I ask you to show it because our next exam covers both chapter 21 and chapter 22. I might have that on an exam. Yeah.
Might have us show H3O plus.
Yeah, our next exam will cover the carboxylic acid derivatives chapter and this chapter, so I do want you to know the mechanism. All right, so now that we've got that, I'm going to, again, redraw this slightly differently. So we've got this R group dangling off here. This time I've got my carboxylic acid with that intramolecular H bond that we know is favorable. And in the next step, this is going to clamp down like this. And the decarboxylation occurs under high temperature conditions. And just like before, this is our enol. Enols are not very happy being enols. They would much, much, much rather tautomerize into their keto form. And we're able to get our desired final product there. Does that make sense? So it's pretty similar to the last reaction, except we're stuck with the ketone at this point. The nice thing with this is once you have a ketone, we can do a lot of chemistry with ketones. So we could add Grignard reagents into them. We can do a Wittig reaction. We could do a reduction, turn it to an alcohol. There's a huge number of things we can do here. So it's a very powerful intermediate. All right. Let's try a challenge one. And I think that's probably where we'll stop today. And what I may do is let you guys work on this challenge one for a little bit, and then I'll post the key in OneNote later. See, so 2, 4, 6, 2, 4. All right, in this reaction, we've got diethyl adipate. We've got sodium ethoxide as our base. Step 2, we have methyl iodide. And then step 3, we have acid and heat. So then the question is, which product will result? And I'll give you a hint. It forms a ring. So I want to see if you guys can work through this, but this is a good practice problem relating all of the alpha chemistry we've been covering both today and yesterday. So if you can, try to work through this with a partner and see if you're getting the same answer. And like I said, I'll post the key on OneNote later, but I wanted to give you about 5 minutes to work on it. Also, as far as the pod goes, the pod is pretty challenging. It is worth 5 extra credit points because it's so challenging. So if you are completely overwhelmed, you don't have to do it. If you want that extra challenge, more power to you. All right, I'll stop it right here.